And the last thing that we do in this unit is a focus on solving trig equations when there's identities. We've done a bunch of these already, but there's a lot of strategies that sort of overlap. So we're going to just focus on it a little bit to get really good at solving. This unit started with solving. It overlaps with chapter 6 in solving. So write these strategies down, and we're going to look at how we can use these strategies in different situations. I'm just going to scroll down so that you can also write out the first question we're going to do. How are we doing? Is everybody done? So first of all, the strategies. I always like the first strategy first. If you can write something with only one trig function, that's very powerful. Can you change everything to sine, everything to tan, everything to cos, everything to cosecant? It doesn't matter which one. That can be very, very powerful because now you're solving just with one thing and you can use all of your algebra skills. Sometimes you can't do that, okay? If you can't do that, then the next two bullets come into play. You might have to change things to sine and cos and eliminate any fractions. You might have to factor out something in common. So in this case, I'm going to change cotangent to cos theta over sine theta. That creates a fraction, but you can get rid of a fraction in an equation by multiplying. For example, if I multiply this side by sine theta, then I have to multiply this side by sine theta. My sine theta on this side would simplify, getting rid of the fraction, and I'd be left with only cos theta equals 2 cos theta sine theta. And there was one very similar to this on your first take-home quiz. Okay. I'm going to just write a note off to the side. Some of you You made this mistake on your first take-home quiz. So here's the note. Some of you on your take-home quiz went, ooh, what do I do here? Well, if I divide everything by cos, it cancels out. That makes it simpler. I should do that. Not a bad strategy, but the problem with dividing is sometimes when we divide by something, we don't realize that we might be dividing by 0. And dividing by 0 is not allowed. In this example, if cos is 0, the left-hand side would be 0, the right-hand side would be 0. That's going to be a solution. And if you divide by cos, you'd actually divide out one of your solutions. So, in the case where you think I should divide, tell yourself, no, I should factor instead. Factoring and dividing are very similar, but factoring doesn't get rid of solutions, dividing does. So what does that look like in our example? Well, I'm going to make one side equal to 0, because if you're going to use a factoring strategy, you have to make one side equal to 0, and then you can factor out the common factor of cos, leaving you with 2 sine theta minus 1. Remember, factoring out a cos out of this first term doesn't mean you're left with 1 cos theta. The cos comes out, you're still left with the 2 and the sine theta. Then, now that it's factored, either cos of theta is equal to 0, or sine of theta is equal to a half. Cos is 0 at pi over 2 and 3 pi over 2. Sine is equal to a half at pi over 6 and 5 pi over 6. And at this moment, I solved my solutions between 0 and 2 pi. I should do a quick check. What was the domain? Oh, good. It was between 0 and 2 pi. So I don't have to change anything here. Example number 2. Again, I'll give you some time to write this down first. Hopefully, you might still have room on 666. You might be going to 667. If you're running out of room, maybe there's room on the next page. Do you mean we go, Carson, you want me to go back for a second?
No.
You're good? You sure? Okay. One of the problems that we run into now that we've learned about the double angle formulas is there will be some questions. When we had a 2x, sometimes that was a multi-revolution question, and now sometimes it's going to be a double angle question. So I have this slide just to help you realize when should I solve something as a multi-revolution question, and when should I use one of my double angle identities. So first, for multi-revolution questions, if you have a solving question with a 2x, 3x, 4x, something inside curves, in particular though we're looking at ones that have a 2x in them, because you could possibly use one of your double angle formulas. But if the only thing you have in the solved question, the only trig function you have is the cos 2x, then you will solve this like a multi-revolution question, where step 1, we rewrite the domain for 2x, which is now twice around. We solve for 2x. When is cos root 3 over 2? That's your pi over 6 family in quadrant 1. And cos is also positive in quadrant 4. Then you would solve for x by dividing everything by 2, which is the same as multiplying by a half. So there's a little review of multi-revolution questions. But sometimes you will get, as we have in our second example, a 2x inside of a trig function, but you have another trig function in the equation as well. So in the example on the right, you have sine 2x, and on the other side you have sine x. So we have the double angle and another trig function. When that's the case, you will always go to one of your double angle formulas. The only thing I can change sine 2x to is 2 sine x cos x. And now I have an equation with more than one trig function, so I have to think of the strategies. Can I change everything to just sine or just cosine? Unfortunately not. You can change cos squared to 1 minus sine squared, but you cannot change cos to 1 minus sine. So then I have to go to the other strategies. Can I factor this? Yes. But first of all, I'm going to move everything over to one side and make another side equal to 0. I have a common factor of sine. So I would get sine x is equal to 0 and cos x is equal to a half. Those are all values on your pi plate. Your y coordinate is 0 at 0, pi, and 2 pi. And cos is a half. That's your pi over 3 family in quadrant 1 and in quadrant 4. And now we'll turn to example 4. So example 4 has a double angle, but it has another trig function. So that's telling us we need to substitute in using the formula. The 2's will simplify here. And we have something in common, so we can factor, leaving us with sine x minus cos x equal to 0. Now when it's factored, this part is easy. This part is a little bit different. It has a sine x minus cos x. And if you wanted that to be equal to 0, that only happens when this is true, when sine x is equal to cos x. So first of all, I'm going to do the left-hand side because it's easier. When is cos equal to 0? That's your x coordinate at pi over 2 and 3 pi over 2. But when is sine x equal to cos x? There's two ways you can do this. One is you can think about your pi plate. Since sine is your y coordinate and cos is your x coordinate, are the x coordinates and y coordinates ever identical? Yes. At root 2 over 2, root 2 over 2. And also down here, negative root 2 over 2, negative root 2 over 2. So You can just think about your pi plate on this one and solve it this way and say that happens at pi over 4 and at 5 pi over 4. Quadrant 1 and quadrant 3 is where my x and y coordinates are identical. The other thing you could do on this one is if you divided both sides by cos, you would get sine x over cos x equals 1, which is the same as saying tan x is equal to 1. And then you're back to your pi plate. When is tan equal to 1? That's my pi over 4 family, and you would get exactly the same answers, pi over 4 and 5 pi over 4. So there's two ways that you could go about solving this one. Okay, now, in your textbook, I want you to circle questions 12, 13, 14, and 15. And if you're looking for additional practice solving equations, on your proofs page, on the back is a ton of solving questions. Okay? So if you want more practice solving, I would like you, this is confusing because there's some circled on here, but they're not the ones I'm going to get you to circle. So take out a different color, and I would get you to, on there, circle 8, 9, 11, 12, 14, 15, 21, 27, 29, and 31. So these are on the handout that you have already. The solving questions, they are probably the most common question on the final exam because they happen in 2 units. So there's lots of practice seeing a bunch of different equations.